Click the bell icon to get latest videos from Ekeeda.
Hello friends, today we are going to discuss to begin our process synchronization topic with a problem known as critical section problem. We will discuss this, what is a critical section problem, how to address this critical section problem, and what are the advantages or disadvantages of taking preemptive and non-preemptive kernel as a solution of this critical section problem. Suppose a system contains n processes from P0 to Pn-1. They all processes had a special segment of code known as critical section. In this section, they may update the common variables value, they can write to the files or update a table and so on. Now, the situation is while a process wants to enter or enters its critical section, then no other processes are allowed to execute in its critical section. Thus, simply, no two processes can execute their critical section simultaneously. Now, this critical section can be entered by giving only or requesting for the permission to enter this critical section. So, any code that implements a request for seeking permission to enter the critical section is known as entry code, which is followed by the critical section, and again which is followed by a exit section, and the rest of the code is the remainder section. So we will see that how a syntax of this critical section can be implemented in a normal C or C++ code. So this is the general syntax of a critical section in a program. First, we are having the entry section, according to which we will enter the critical section, and we will follow it by an exit section, and the rest of the code that will be programmed is known as a remainder section. Now, this implementing critical section is designed to protocol to use the processes cooperate among each other. Now, to solve this critical section problem, there are three conditions which should be kept in mind. The first one is the mutual exclusion. That is, if process Pi is executing in the critical section or has entered the critical section, then no other process can execute or enter their critical section. The second one is progress. If some processes or a single process is executing in its critical section and there are a number of processes which are waiting to enter its critical section, then the processes which are not executing in the remainder section of the code are only allowed to participate in the decision that which process will enter the critical section next. And this decision can be postponed indefinitely. The last one is a bounded waiting time. There is a bound or limitation on the time that the number on which the number of the processes that are entering its critical section after it has requested for enter the critical section till the request is made. Now, if we follow these three conditions, then we can achieve the critical section problem addressing. We assume that each process is resuming in a non-zero speed. However, the concerned relative speed of n processes cannot be assumed. Suppose that a kernel data structure processes several when running in the kernel mode of the operating system. Thus, the operating system is prone to several possible crash conditions. Now, for example, if a kernel data structure which is maintaining a list of open files and there are several processes which wants to access these open files. Now, if two processes wants to update and open the file simultaneously, then results will occur in the inconsistency of this list of opening files. as the updation of this removal and entry of the list of opening file data structure will provide an inconsistent result if the processor do two simultaneously. Now, the more processes or data structure that are prone to rest conditions are which structures maintaining the memory system, structure maintaining the process management, or structure maintaining the interrupt handling. Now, it is up to the kernel developers to ensure that no two processes access the kernel data structure simultaneously. Now, there are two ways to address to this situation. Number one is a preemptive kernel and number two is a non-preemptive kernel. In preemptive kernel, the process that is running in the kernel can be preempted by any other high priority process or any other process that requires the resources immediately. Now, if a process is running and a high priority process is available in the queue, then only the kernel data structure will let preempt it the running process. A non-preemptive kernel does not allow the kernel to preempt the running process and it will allocate the CPU until it blocks, terminates, or voluntarily yields the control of the CPU to any other process. So obviously the non-preemptive kernel doesn't suffer from the rest condition as there is only one process at a time executing the kernel data structures. So no other process can execute or enter the kernel data structure while modifying it by any other process. Now then, why would someone choose preemptive kernel over non-preemptive kernels? As the preemptive kernels must be carefully programmed because it is very difficult to implement its SMP architecture as the two processes can run on two different processors simultaneously tries to actively access and kernel data structure at the same time. But we choose the preemptive kernel over the non-preemptive kernel because they are very much responsive than the non-preemptive kernel. Suppose a user wants to apply to an application and it is a real-time event, then it will be preempted by any other processes which are running in the kernel. That makes the application and the operating system more responsive than the non-preemptive kernel one. And also it occurs a less risk that a kernel would acquire by a process for a long time after relinquishing the process to preempt by any other processes. So in this way, preemptive kernel is more acceptable than non-preemptive kernels. And these situations can be addressed to address the critical section problem. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.